Hear me? So we start now with this session. As IACS President, it's a great pleasure to introduce the first speaker in this session of Union Lecture. There are 3 talks. The first talk is given by Ricarda Winkelmann, and she's professor here at the University of Potsdam and the Potsdam Institute for Climate Impact Research. Ricarda is well recognized for her work that includes Greenland and Antarctic ice dynamics. She has received numerous awards, and I look very much forward to her talk. The floor is yours.
Yeah, thank you so much. It's an immense honor to be speaking here at the IACS Union Lecture this year. And I'm very grateful for the opportunity and also super happy to just see you all, because none of this work would be possible without this amazing community. I think we can all agree that we're living in extreme times. Just this past week alone, the world's hottest day record has been broken actually 3 times already. And there have been numerous more regional heat records, like for instance in Africa, where the hottest night was recorded last week with temperatures that never dropped below 39.6 degrees centigrade in Algeria. And these heat waves are attributed to climate change, but also an emergent El Niño pattern. So these are extremes that we're all experiencing at the moment, but of course extremes are also occurring in the polar regions. So for instance, in June 2020, the hottest temperatures in the Arctic have been recorded with plus 38 degrees centigrade. So that was 18 degrees warmer than the average maximum daily temperature that was in June before. And then at the other pole, in February 2020, there was a heat record of plus 18 degrees at the Antarctic Peninsula. And then just last year in March, there was a temperature record at the research station Concordia in East Antarctica with almost 40 degrees warmer temperatures than normal. And if we just look at the most recent observations from Antarctica, there's, for instance, a record low in Antarctic sea ice extent just this month alone. Of course, this affects our sea level giants, the ice sheets on Greenland and Antarctica. And the reason we can call them sea level giants is in their sea level potential. So if we were to take the ice volume of the Greenland ice sheet, and if it were to melt completely and we distributed this over the global ocean, then sea levels on average would be raised by more than 7 meters. And for the Antarctic ice sheet, it's even 58 meters of sea level potential. So it's very significant what happens with the ice sheets, and it actually has consequences for coastal regions around the world. Now, over the past decades, both ice sheets have been losing mass, and they've been losing mass at an accelerating rate, where most of the mass loss at the moment for the Greenland ice sheet is happening around the margins, and for the Antarctic ice sheet, in particular for West Antarctica. And with these recent mass loss changes that have been recorded, we're actually right now tracking the highest climate emission scenarios. So as you can see here, this is a comparison of a lower scenario as per the last IPCC report, medium scenario, and then an upper scenario. And what you see in gray, those are the observations. So right now we're tracking that highest climate scenario. Now, what makes this so important for us is, of course, the direct consequences that arise from this in terms of, for instance, sea level rise, also the secondary effects through changes in our coastal currents, regional sea level rise, groundwater saltification, and so on. But more importantly, with the ice sheets, there are a number of so-called positive, so amplifying, and then negative dampening feedbacks connected. And here you see an overview of such feedbacks. Most of them are really well known, like for instance the ice albedo feedback, but there are some that are particular for the ice sheets, and we will go in a bit more detail about this in this lecture. And because we have this very complex interplay of the positive, so amplifying, and the negative dampening feedbacks, The future stability of the ice sheets on Greenland and Antarctica is actually a really important topic to consider. If we just look at the last IPCC assessment report, in the synthesis report, it says, and I quote, "The likelihood of abrupt and irreversible changes and their impacts increase with higher global warming levels with high confidence." And then risks associated with large-scale singular events or tipping points, such as ice sheet instability or ecosystem loss from tropical forests, transition to high risk between 1.5 to 2.5 degrees medium confidence, and to very high risk between 2.5 and 4 degrees with low confidence. So this already tells us that the ice sheets, among others, are part of the tipping elements in the climate system. So there is a potential for abrupt and also a potential for irreversible changes from the ice sheets, as for other systems, like, for instance, the tropical forests that are mentioned here. But we also see that when it comes to actually pinpointing when or at which temperature levels such tipping points occur, we still have low confidence. There's still a lot to understand in order to really figure out what is that risk zone for the ice sheets in particular and other tipping elements as well. Now, we have a really good understanding of the processes that can lead to such tipping dynamics. And while, of course, for both ice sheets, the physics that are governing the ice sheet dynamics are the same, there are two different feedback mechanisms that are dominating this complex balance when it comes to especially the positive, the amplifying feedbacks. For the Greenland ice sheet, this is connected to surface melt. And here you see some observations. This is from Operation Icebridge, where you can see these meltwater puddles forming at the surface, which then actually even flow into rivers, and eventually they can form moulins, so basically waterfalls that go deep into the ice sheet interior, and that can really have a significant influence on the ice flow and the ice dynamics in general. And with this surface melting, which has not only increased in general in Greenland, but where we've also experienced a number of extreme events in the recent decades, there is one of these positive feedback mechanisms connected. And we all know this, the main mechanism we know from mountain climbing. So if we hike down from the peak of a mountain to the valley, then it gets warmer around us. That's just the atmospheric lapse rate. And the same also happens with the ice sheet surface. So as it lowers into lower elevations, for instance, through enhanced surface melt, there is a possibility that the temperatures at the surface increase, thereby increasing the melt at the surface, which in turn could lead to a further lowering of the surface, and so on and so forth. So this is the so-called melt elevation feedback, and this is one of those positive amplifying feedbacks that could potentially trigger tipping dynamics for the Greenland ice sheet. So this is something that has been recognized for a long time. This mechanism is quite well understood. The question now comes when we think about this feedback mechanism and all the other feedback mechanisms and how they balance each other out. So the most recent estimates say that there is a potential for abrupt change and even collapse of the Greenland ice sheet on the very long term at temperatures between 0.8 and 3.2 degrees of warming. Those are the most recent estimates. And once such a critical temperature level is crossed, without any additional warming or changes in the climatic boundary conditions, the ice sheet could potentially keep losing mass until there's only small ice caps remaining in Greenland. So this is something that, as I said, has been quite well understood in terms of the mechanisms. There are also a number of modeling studies that have looked into this. And there's even evidence from paleo records that show that Greenland must have been ice-free in certain periods of times. And the rates with which the ice sheet has lost mass are consistent with such a feedback taking place. And because of this and other potential positive feedbacks, this is why we are considering the Greenland ice sheet as one of the crucial tipping elements in the climate system, where because of these feedbacks, we have phenomena such as hysteresis. So as it's depicted here in this sketch, there's a potential for multiple stable states. And the question is, however, at which point, and also at which point in time, could such a tipping point occur? Now, for the Antarctic ice sheet, it's quite different, because in Antarctica, it's a lot colder than in Greenland, so there is less surface melt in general at present. Nonetheless, the Antarctic mass loss has tripled over the past years, especially in the Amundsen and Bellingshausen sea regions in West Antarctica. And the reason for this are the ice-ocean interactions. So modified circumpolar deep water entering ice shelf cavities in West Antarctica, which could then lead to enhanced ice shelf thinning, and this is also what's observed, which in turn decreases the buttressing, so the backstress at the grounding line that's hindering some of the outflow into the ocean. So in turn, this all could lead to accelerated ice flow. And this is also what's been observed, for instance, after ice shelf collapses, like for the Larsen ice shelves. One could observe that after the ice shelves collapsed, there was a significant speed up of the flow into the ocean. And as we can see, there are, especially in the Amundsen and in the Bellingshausen sea region, the ocean temperatures are already a lot warmer than in some of the other areas like the Weddell Sea or the Ross Sea. But of course, there is potential that this could change in the future, either through changes in the ocean currents or through actual warming of the ocean, of the Southern Ocean itself. And with this, there's another positive feedback mechanism connected, and this is the so-called marine ice sheet instability. So marine ice sheet basins are basins that are grounded below sea level, as depicted here, for instance, in this cross-section for West Antarctica. But as you can see on the right, there are actually a number of regions also in East Antarctica that are such marine regions. And in the case that in such a marine ice sheet basin, the grounding line, so the separation between the grounded ice and the floating ice shelf, sits on a so-called retrograde sloping bed, so one that becomes deeper further inland, there's a potential for an instability mechanism which arises through an initial grounding line retreat, which could, for instance, be caused by additional subshelf melting, but also by changes in the surface mass balance or other dynamic processes. So if you have this initial retreat of the grounding line, then the ice at the grounding line is going to be thicker on this retrograde sloping bed, which could lead to enhanced outflow across the grounding line, and that in turn leads to further grounding line retreat. So you can see that there's another one of these amplifying feedbacks connected with the grounding line retreat. And since some recent observations from the last decades show that the Amundsen Sea region in particular, which is one of these candidates for the marine ice sheet instability, there has been retreat of the grounding line observed already, and also a thinning of the glaciers that drain into the Amundsen Sea in this region. There has been this question whether potentially the Amundsen Sea basins might already be undergoing a marine ice sheet instability. So with a team of researchers using 3 different ice sheet models, we looked further into this and basically tried to detect whether right now already the marine ice sheet instability might be governing this retreat of the grounding line. So the question is, if we were to reverse the current forcing, would this lead to a reversal of the grounding line retreat that is currently observed, or could the grounding line potentially re-advance? And what we find is quite a complex picture where, on the one hand, right now we can say that the present-day grounding line retreat is driven by the external forcing, in contrast to the instability. So that means if we were to reverse the past history of climate change in the Antarctic region, then the grounding lines could also re-advance. But at the same time, if this forcing is not reversed, so if we just fix present-day boundary conditions, then on the really long term, so millennial timescales, we find that parts of the Amundsen Sea embayment, especially the glaciers that we had just looked at, could potentially already be committed to retreating further and even leading to a partial collapse of the West Antarctic ice sheet. So this is quite a complex message, but basically it says that while right now there is still the possibility for reversal, at the same time changes might already be triggered that will then unfold over much longer timescales. And if we zoom out of the Amundsen Sea region, we can look at the overall stability of the Antarctic ice sheet. So what you will see now is an animation showing what happens if we keep very slowly increasing the global mean temperature. And the reason these experiments are done in this way, where we increase the temperatures very slowly, is so that the ice sheet can stay in quasi-equilibrium. So we always want to look at the long-term quasi-equilibrium response of the Antarctic ice sheet. So these are not projections in the typical sense, but really stability experiments, if you will. And what we see is that with increasing temperatures, you first of all see a retreat in the West Antarctic ice sheet, and there's a first major threshold right now, somewhere around 2 degrees of warming, where large parts of the West Antarctic ice sheet collapse. And this is mainly driven by this instability mechanism, the marine ice sheet instability. As the temperatures further increase, you can see that parts of East Antarctica, so for instance the Wilkes Basin, are becoming unstable as well, again due to the ice-ocean interaction. But then there's a second major threshold, around 6 degrees of warming, where, as you can see, large parts of the continental East Antarctic ice sheet can also become unstable. And this is where the surface processes become dominant. So at this point, it's warm enough that there is significant surface melt, and for instance, something like the melt elevation feedback can also take place. Now, it's important to consider that, of course, the Antarctic ice sheet has never been ice-free as long as we humans have been around. In fact, it's not been ice-free for many millions of years. So this is a very significant change that we're looking at here for these higher temperatures. What we also find is that there is a true hysteresis behavior, meaning that changes like this cannot be reversed. So if we do the reverse experiment where we cool down the planet again, the Antarctic ice sheet does not regrow at the same temperatures. In fact, as you can see here, the ice volume on the retreat or the warming path and the regrowth, the cooling path, can differ by as much as 20 meters for the same temperature. And for comparison, those vertical lines that you see, they show where we're at in terms of present-day warming levels, and then for the 4 typical RCP scenarios, where RCP 2.6 is the peak and decline scenarios that still stays within the Paris Agreement warming levels, and RCP 8.5 is something similar to a business as usual scenario. You can see the warming levels right there in these vertical lines for comparison. And importantly, it's also the case that temperatures would have to be cooled down to well below the present-day levels to actually really regrow the initial ice volume. And of course, we know that even if the initial ice volume is restored, then this would not be the same ice sheet with the same characteristics as the present-day Antarctic ice sheet. So coming from this continental view, actually looking at the whole Antarctic ice sheet, we can also look at some of the regions or basins within Antarctica. And in a recent study, we're looking at, well, how is this ice loss actually occurring in these different basins for continued global warming? So what you see here are, for the different ice basins around Antarctica, the ice loss per degree of warming. And as we can see, there are some basins that lose their ice volume rather gradually with increasing temperatures. So these are the ones marked in blue here as examples. While in other cases, there really is abrupt large-scale retreat or collapse. And as you can see, the Thwaites and Pine Island Glacier that we just saw are part of this, but so are, for instance, the Totten Glacier as well as Amory ice shelf. So in these regions, there really is possibly ice loss that's driven by the instability rather than the increased forcing levels. We all know that these changes in the ice sheets have a long-term legacy, and that's why I think it's important that we consider this also in our projections and in the communication about changes in the ice sheets. Because there is a significant difference between the typical projections that we look at, for instance, in the IPCC report, where we look at timescales until the end of the century or potentially until the year 2300. But we do know that the bulk of sea level rise from changes in the ice sheets would actually occur thereafter, so beyond the 21st century. So what we're looking at here is the so-called committed ice loss. So ice loss that might already be triggered in the coming decades, but then unfolds over much longer timescales. And there are two reasons why this commitment, the committed ice loss occurs. One, there's of course high inertia in the ice sheets, so the response timescales of the ice sheets are quite long. But then at the same time, we have these potential tipping points that might be crossed and could lead to irreversible changes as well. So here, just as an example, if we look at just at the Antarctic ice sheet, you can see the difference between the typical projections and then the committed ice loss. So to the lower left, you can see maps for the years 2100 and 2300, where the left column always shows the projected ice loss, so what we would typically see in the IPCC assessment report. And to the right, you see the committed ice loss, so ice loss that's already triggered within that timescale, but then takes longer to unfold. And as you can see, there is a huge difference or commitment gap between these two curves. And this is the case for Antarctica, but also in the same way for Greenland as well. So in a way, we need to consider this because we're kind of living these two worlds, where on the one hand side, we're looking at the already actualized, the already realized changes in projections, but then we should also consider the committed changes. And this is not only true for the ice sheets, but it also refers, for instance, to terrestrial carbon changes. So what you can see here are, again, the projected changes in ice thickness for Greenland and Antarctica. And as you can see, by the end of this century, they are quite low on this scale. And you also see the changes in carbon and terrestrial carbon that are projected by the end of this century. And now if we compare this with the committed changes, you can already see that for the ice sheets, there is a significant difference between the projections and the committed impacts. And we can take this one step further by also considering one of the major uncertainties when it comes to vegetation changes, and that is the CO2 fertilization effect. So in this case that you see right now, these are changes that are done with basically just continued strong CO2 fertilization. But if you go with a much lower CO2 fertilization, basically setting them to the current levels that we have, then this picture again changes drastically. And these are the committed changes, the two worlds that we're looking at. So as I said, because of these committed impacts, these potential irreversible impacts, the ice sheet, as well as parts of the biosphere, as we just saw, are considered tipping elements in the climate system. And as you can see, there are a number of more potential candidates for such tipping elements. And there has been a lot of work done in the international community over the past years, trying to assess in how far and at which temperature or other climate change levels such tipping points could occur. And these are the most recent estimates put together from literature, and this includes different sources of, or different lines of evidence from individual modeling studies, from observations and early warning science, and as well as paleo evidence. So if you put all of this together, then you can see that there are already a number of tipping elements which are at risk of crossing a critical threshold when global warming levels exceed 1.5 degrees centigrade. Now, just as a reminder, this line right here, this is the current warming level of a bit more than a degree in comparison to pre-industrial times. And what you see in gray there, these are where we would get with the current policies. So this is where we're heading at the moment with the different pledges from the nations around the world. So as you can see, we're actually moving into that risk zone, especially when we consider where we might be at the end of the century under current policies. And you can also see that Greenland and West Antarctica are really among the most vulnerable tipping elements in the climate system. Now, of course, these tipping elements are not in isolation, but they interact with one another, as the entire climate system is a very complex interactive system where processes happen at various timescales and spatial scales and really influence each other. So one way of looking at the interaction of tipping points is to use network approaches to assess the overall stability that arises. If, for instance, we say we have one tipping element that crosses its critical threshold, and given all the knowledge that we have about timescales, the critical thresholds themselves, the network structure and topology, we can then try to assess with complex adaptive network approaches which influence this has on other elements of the network. And as you can see, there are a number of papers where the theory of networks of interconnected tipping elements has been advanced quite a bit just in the past 3 years alone. And now we can apply this to, for instance, these 4 tipping elements in the climate system, where we have our 2 ice sheets on Greenland and Antarctica, the AMOC, so the Atlantic Meridional Overturning Circulation, as well as the Amazon rainforest. And we can consider and also propagate uncertainties that we have, because we do know that there are large uncertainties when it comes to the critical thresholds or tipping points, when it comes to the network topology, so how do these interact, and then also the interaction strength. So if I do have a significant change for the Greenland ice sheet, then on which timescales does that actually affect the AMOC, for instance? So we use this complex network approach with more than 3 million simulations to basically propagate these uncertainties and get a better picture of the associated risks with potential tipping cascades. And one of the main results is that the risk of domino effects or tipping cascades really increases significantly with global warming. So as some of these could enter their own risk level, this could also affect the climate system as a whole. So this is more of a conceptual approach, bringing together what we already know from process-based complex models. But what is still lacking at the moment is a more systematic approach looking at all of these uncertainties from the critical thresholds and the mechanisms themselves actually to what can we say from paleo evidence, what can we tell from observations on early warning signals. And this is why I proposed something like a tipping point model intercomparison project, the TIPMIP, where we can bring together the expertise in the international community to really look at these questions. So the critical thresholds themselves, can we maybe confine these risk levels? The question is, are changes in some of these systems reversible? And if so, on which timescales? And at which point does it come to irreversible impacts? What are the commitments? So similar to what we've already seen for the Greenland and Arctic ice sheet just now. What is the potential for noise and rate-induced tipping? Because the bifurcation tipping, as we just looked at, is not the only type of tipping dynamics that occur in the climate system. And in the beginning, I talked about the extreme events, and you could consider these as actually something that could also increase the risk of noise-induced tipping. Then, of course, the interactions. So how does this affect the stability or resilience of the climate system as a whole? And lastly, what can we say about early warning indicators? So this is a community project that was just launched and that we are working towards in the coming years. And I think it's really high time that we bring together the expertise on all of these different questions. And with that, I would like to thank you very much for your attention, and thanks again, once again, for this opportunity.
Okay, so the next speaker will talk about hydrology, and I'm very happy to introduce Adriana Cuartas, who is currently a scientist in hydrology at the Brazilian National Center for Monitoring and Early Warning of Natural Disasters. So Adriana, she has a background, she's graduated in hydrology, but she also holds a PhD in meteorology. So she's really a role model when it comes to interdisciplinary research. And today, she is working mostly on understanding and predicting extremes, hydrological extremes, like drought and floods. And I think today we will hear more about predictions in drought, which is very timely as we have a severe heat wave in Europe at the moment. So thank you very much. Adriana, please welcome.
Okay, thank you very much. Good morning first, and I would like to thank first for the organizing committee to inviting me here, and also France. And maybe today I will not talk much about droughts, but also floods and other things. For me, it's a great pleasure to be here and be able to tell about our development of hand models. This study, this research started, I think, almost 20 years ago when I was starting my PhD in Brazil, but I'm from Colombia, by the way. This development was led by me and Antonio Nobre. So I will divide my presentation in 3 parts. In the first one, I will talk about the insights, hypotheses behind the hand development. Then I will explain what is that normalized hand model. And finally, I will show you some applications around the world. Okay, let's see. Okay, so our first insight, this is, okay, the counter is, I think the counter is from you now. So here is the first insight that we had there. So this was thinking about the similarities on the hill slope and different height above sea levels. So we know that they have some similarities. For example, if we look at the Amazon Delta River, so a few meters above sea level, compare, for example, with a catchment or river in the Andean Mountains, that is almost 3,000–4,000 meters above sea level. So we see that we can perceive that typical soil environment repeat across landscape, and apparently weakly or not correlated with this height above sea level. Okay, the second one was that the surface water is as a distributed proxy of groundwater. So that means because we know when we have a perennial river, we know that the water table there is at the surface. And of course, the soil are saturated in that point. So, and that occurs independently of the height above the sea level. So it's happened everywhere. So the string are the indicators of this localized occurrence of saturated soil across this landscape. And as we know, the superficial or this condition, soil moisture condition at the surface is important for water and energy fluxes partitioning in the continent. So it is one of the most important. The third one was about the gravitational potential that drive water flows. So this is thinking about the topography and the gravity generate energy gradients and propel waters downwards. That's it. It's very simple. And the last one was about the water that they move through the landscape. And in each point of the landscape, they have a local drainage direction. So that every point has the direction that the water goes down, and of course the water tracks to the least energy trajectory. So this is the main reason. And of course, all that point are connected through the flow paths in the landscape. And this is very simple, but here is a diagram that shows that all points in the landscape has a, as we say, local gravity or drainage potential or local hydraulic head. So this is where we know. And this explains, for example, why we use the stream or rivers as a base or reference for our model, as we explain later. Here, this is a catchment that we instrumented in Manaus at the beginning. So here we start our work in developing this hand model. We instrumented this catchment in the context of the LAVA and Ecocarbon and Carbon Sink projects. And we have, for this basin, precipitation, soil moisture, interception, water table depth, discharge, among other data. And this data allow us to understand the water table dynamics, the soil moisture distribution in that basin, and also compare and make the correlation with the vegetation and soil types in that basin. Well, now here I will explain how we got the handy model. So we did two procedures to get there. So the first procedure is the same procedures that we do when we need some layers for our distributed hydrological model. So we need what? Topography, but a coherent topography for hydrology. We need this map with the local train directions. We also need the flow paths, so a map with the flow paths, and also the stream network. So this is the first, as this is typical, it's the same for all hydrological model, especially the distributed hydrological model. So the second and the key procedure that we use here for obtain the hand model is that we have to connect, maybe I think it's here, I don't know how to, okay, I don't know, it's working. You can see here? No. Okay. The tension there? Okay. Okay, I can use here. Okay, thank you. So here we can see that all pixels in the topography or in a digital elevation model are connected with one pixel or one cell in the drainage. Okay, so we have this one, through this flow path, and that allowed us to calculate the difference between each point in the topography with the corresponding point in the drainage network. So in that case, we can see here, all pixels in the drainage network became 0. So now we have the vertical distance from the river to each point in the topography, but correlated with the own flow path. Okay? So this is crucial. And here we can see the difference between the handy model, a typical digital elevation model. Here, for example, we can see a gradient between the south with west part and then go up to the northeast. But here in the handy model, this gradient disappears, as we can see here. So the model now is reference to the drainage and not more to the height above sea level. Here is an image of 2D plot that is, I think, is easier to see the difference. And we can see also that the elevation change, the maximum and minimum elevation changes. And here, all drainers are 0. So this is why we call it a normalized terrain model handy. This is the name of this. And finally, also, we classify this handy model using our data of the Azure catchment in Brazil. So this data allowed us to calibrate these environments that are correlated with soil condition. So here we can see the blue areas are the saturated blue and green are the saturated soils with the water table close to the surface. And the yellow and red areas are the areas that are not permanently saturated. So the water table is deep. So this classification also is not fixed. It's a classification that we found for that catchment that apply for many other things, but it's possible that the users can change according with their own interest. And of course, we want to evaluate the applicability in a large scale. So we validated those handy classes for a largest enclosing area close to the Negro River in the central Amazonia. So here we can see a landscape image, but we can see here only the forest, the main river, this is the Rio Negro River, and part of the Manaus city is over here. Only that, okay? But when we look at the topography, we can see more details, especially in terms of rivers. We can see more interesting detail, but the problem is from here we cannot easily extract quantitative hydrological information, certo, for this topography. But here we have the handy normalized topography or topology, that is the local drainage potential. All the height here at this is a hydraulic head. So this is now we can extract more quantitative information of hydrological meaning. So, and of course we classify the model, and we can see the difference between this part of the river, this west and south, compared with the north and east part. We can see here more saturated soils when water table at the surface, compared with this area that the water table is more deep. So we can see all those differences. Here, the black area is the map are the seasonal fundable areas. So we don't consider this for our estimations or validation. And of course, we went further and we mapping all soil environment for South America. So we use only topography, as you know now, and this is a 1 kilometer resolution for mapping, so we can see some specific areas. For example, this Pantanal area is a wetland in Brazil. This is a Tocantins area. We can also see the Andean mountains perfectly here, so we can see some geological features also here. And this work, it's the well-known of the Funk and her colleagues that they published in Science. They simulated the water table globally, and they use topography. And for South America, they use more than 30,000 well sites in Brazil, in South America, sorry. So we can see here the similarities between both maps here. And later on, the same co-author Funk made this statement that the Handy is an elegant topographic proxy to capture the spatial patterns of water table depth. So this was interesting. Now I will show you a handy model application, how it's applied now. And of course, the first application was in my PhD, of course. So I was interested at that time to understand the hydrological processes in this fine scale and how is drive the large scale processes. So I need made some simulation of the hydrological processes, but how to do physically based distributed hydrological modeling with coarse resolution data. At that time, I only have this data at 1 kilometer. So what type of soil for that area, and one type of vegetation. So I went to the literature and made all of this study. They define the soil, the soil of type for all these environment that we already mapped with the handy. So for each of one, we know what kind of type of soil there be. So that would be able to create high-resolution soil vegetation maps. These maps are 30 meters resolution. So we have here a soil with the 4 types of soils for that region. And also for vegetation, we know in the Amazon the vegetation that is close to the water table, or when the water table is at the surface, it's quite different to the other vegetation. In the Landsat, it seems the same, but it's not. So we have 2 types, a little bit of vegetation, so it's important. So we can, now with this data, we can simulate the soil moisture distribution, water table depth, and also a discharge. And we obtain a set of parameters for those kind of soils and vegetation. So this was important. And here is some of the work that they use our data, our parameters, and they say it as a representative for that area, but they are using for another areas. They use here for a land surface model. So they use our parameter for a land use surface model. And here is a conceptual work that propose to use the hand to represent the heat slope in Earth system models. See? So they are proposing to divide grid cells into zones with the linear Reynolds relation using the handy model. Okay, here is another application, and this is for flood hazard mapping. So we developed the handy contours that we call like this. And here the insight was when the rivers overflow, they normally take the way or the path that they supposed to take when they came to the river by the surface. So they go out, and so they go up hills, following, of course, the flow path. So it was the same concept here, but this is the opposite. Now it's the water that is going up. So we developed these hand contours that this is isolines. So isolines of equal height of the hand model. So it's like this. So it did allow us to, for example, map flood hazard levels, uses these intervals. So or you can use your intervals depending on what do you need. Here is an event that we used to develop the hand contour, the study. This is a case study in Brazil. The name is Itajaí River. It's in the south of Brazil. This region has a lot of problems with floods, so we use this as an example. And this here is the inundation predictions using the hand contours and also compare with the observed. And so the observed flood here is in blue, and the hand is about this map, but we can see, for example, in some areas we have a overestimation, another that here in gray, and another we have underestimation, but in general they match pretty well with the observed map. And here we can use the height of the hand and the opposites to look the depth of the water during the flood. So this is important, for example, for rescue when we have a disaster, for example, and we can use also for mapping the vulnerabilities in that region. So know what is the vulnerability of the people there. So this is interesting also. And here is one of the applications. The result is for the master thesis in Colombia. And you see it here, this is the point, the red point where the people say that the flood arrived and hit that point. And in blue is the handy map. And in this case, it's for 20 years return period. So that match pretty well also. And here is one of the many words that you compare these proxies for mapping floods, and they compare handy with hydrodynamic models and also with some topographic index and something like that. And here is one of the words that they proposed a combination between hydrodynamic models and the handy model like here. So it's one of the approach, but there are many others. It's only a few examples. And here is the MERIT, the Global Hydrological Dataset, I think you know, was generated by Yamasaki. And one of the layers there is the handy model and 90-meter resolution. So now it's available for all the continent, for all the planet, and that resolution. So we can just go there and download the data for your region. And here is they are using for mapping flood risk area in the United States. So they are applied our model there. So this is one of the examples. And of course, we developed a software. This software is free, is in English, and is compiled for Windows, Linux, and Mac, so can we use for everyone. But of course, there are other groups that develop their own software. And here is one example. They did, this author did a plugin for RGs. So they are also available for RGs for application over there. Well, our papers have strongly influenced the field. We have made that when we developed in the hand, so more than 1,000 citations in our paper in many, many disciplines and areas, but it influenced more than that we expected at that time when we developed, so this impact a lot the land surface science. So here, my final considerations. So the handy model is an effective tool for uncovering hiding saturated soil or water, thereby acting as an indicator of groundwater table. As a flood risk mapping technique, the handy contours can anticipate the possible inundation boundaries in the channel that convey the floodway and those areas influenced by that flooding. Of course, the handy model is universally applicable, so to any location with available digital topography. So we can apply here in the Earth, on Mars, or wherever you want to apply. The evolution of the handy model highlights the necessity of integrating first principles or the physics of the process in a comprehensive manner to improve our understanding of surface processes. So the handy concept is quite simple, but it's powerful. So thank you very much. Question? Maybe the next one.
Okay, good morning, folks. I'll introduce myself. Oh, sorry.
We're going to have to fire you, Ravi. So, I'd just like to say, Mary Scholes and myself, John Burrows, we're Vice Presidents of IAMAS, and we're here to introduce Ravi. It's our great pleasure to have Ravi here as a speaker. He's a very famous international scientist. He began his work in India, moved to Florida, and then moved around the United States, Georgia Tech, also University of Maryland, doing good research. He spent many years as part of NOAA, where he scaled up the ranks and became one of the leaders of the NOAA, very famous NOAA, and now it's called Earth Systems Laboratory. It used to be called the Aranami Lab, and he was one of the leaders of that for many years. He then decided to go back into academia, and he's currently at Colorado State University. He's most famous for being one of the pioneers of modern reaction kinetics, both of gas phase and multi-phase. But more recently, he's got into modeling, and as part of the UNEP WMO, he became interested also in societally important science, which is, for example, the ozone depletion, okay? And now, in this sense, he's moving into a new area, which he's going to talk about, or he's moved into a new area, which he's going to talk to us about today. It's really a great pleasure. Ravi's not only a good friend, he's one of the greatest scientists I know.
Thank you, John. I would have had a much shorter introduction. I'm Ravi. Okay. First of all, thank you for the invitation and the opportunity to talk to you. Can you all hear me okay? Okay, great. Apologies to atmospheric scientists, because I'm going to simplify things. there is actually science behind some of the stuff I'm going to tell you, but I just want to tell you a reasonably simple story. And the question I'm asking is, are the people in developing countries paying with their lives to reduce climate change? The answer to that, you don't have to wait. The answer is yes. You need to restart it, of course. Okay. So the bottom line is, what I'm going to try to tell you is, you have to think about not just what we are emitting into the atmosphere, but we really need to think about the cumulative amount that you have put into the atmosphere. The legacy does matter. Second, as much as we are focused on greenhouse gases, which is very important, there are other things that are also important, specifically aerosols. In the climate science, we call it aerosols. In health science, you call it particulate matter, PM. And then you look at what the interactions between those two are. And then we'll just tell you a little bit about what kind of action is needed, and a kind of a taste we got for that during the COVID. So, the first thing I want to do is to dedicate this talk to Dr. Daniel Albertin. If many of you might have known him, he was an amazing scientist, an amazing communicator, not only with scientists, but with policymakers, and a superb administrator. And he passed away earlier this year. And he was actually a great mentor for me and a personal friend. And it's a loss that it's difficult to explain. Okay, so first concern, human activities are increasing greenhouse gases. That's well documented. You can look at on the left-hand side on that the picture of carbon dioxide, methane, and nitrous oxide. You can plot a lot of other things. You could plot number of McDonald's or the number of people. They kind of all look the same. It was pretty constant for quite a while, especially, and then over the last 100 years, it's actually exponentially increasing. And if you look at carbon dioxide itself, there's the Keeling curve, started by Keeling at Mauna Loa, and now continued by NOAA Israel Climate Monitoring Lab now. And this actually is an amazing picture. What you can see is that it continuously is increasing, and you can see the cycle of carbon cycle in the atmosphere. So this is one of the major causes of climate change. Now, but humans, while they've been doing greenhouse gas increases, they have also increased aerosols, and aerosols are very tiny particles. They're very short-lived in the atmosphere. Specifically, I'm going to talk about something called PM 2.5. There's particulate matter of diameter less than 2.5 microns. You can argue about how do you define a diameter, but we can talk about it. It kind of gives you an idea how big those particles are. And what you can see on the right-hand side is a human hair. You can pull one out and look at it. That's what I don't have any hair anymore. Anyway, and you can see how many of those you need to put around a human hair. These things do not accumulate in the atmosphere because they don't last as long. They last for maybe a few weeks at most. They also absorb and scatter radiation, but the most important thing is they actually scatter radiation and affect clouds. So they have this kind of influence. Overall, they reduce the effect of solar radiation coming in. And I'm going to talk about, in terms of the health, of my metric for using it is something called premature mortality, but there's more than that in terms of what happens. So just think of premature mortality I'm going to show you as a metric for the health impacts. The work that has been done here, mostly my colleague Dan Murphy, who's still at NOAA Israel, CSL, and Ligi David. She moved away from CSU a couple of years ago at Utah State University for another week, and then she's coming back to Fort Collins. And many other colleagues, specifically Jeff Pierce, an amazing colleague of mine at CSU, Chandra Venkataraman from IIT Bombay, and a few other people I have mentioned here. Many of the things I'm going to talk about has been published over the last 4 years, but that's not the key point though. I just those are the bricks, it is there, but I just want you to see the overall picture of what's happening, okay? So, greenhouse gases warm the atmosphere, warm the planet. Aerosols overall cool the planet because they scatter radiation either directly or through the formation of clouds. So what matters is the net amount of this, what happens with greenhouse gases and with the aerosols. Okay? So the other way of thinking about it is aerosols have actually masked the full effect of greenhouse gases. They have reduced climate change. So we focus a lot on emissions. So if you were to look at the emissions, for example, on the left-hand side of this picture, you don't have to look at it carefully. It just gives you who the current large emitters are. But that's not the only thing you have to think about, because it's not just what they're emitting today, but what they have done in the past. So what you see here on the bottom right-hand picture is the climate forcing. That's the word I'm using. It's actually the radiative forcing, top of the atmosphere radiative forcing, as a function of air from various regions of the Earth. These regions have had similar economic trends, and you can see that North America, which is essentially USA and Canada, have had the largest contribution. And then it goes on and on, Western Europe, and you can see all the other ones. But once you account for the aerosols also, you see a pretty different picture. As you can see, the radiative forcing was actually not that large because the aerosols were offsetting some of it. And of course, then after a while, the greenhouse gases took over, and it's kind of a breakthrough of how it happens. North America cleaned up its air much sooner than Western Europe. And China, for example, is cleaning up its air now, and it's contributing. India is hardly actually coming out as a positive forcer so far. So if you just kind of think about this, if you plot the global radiative forcing as a function of air, what you need is the integrated amount. So think of it as a radiative balance picture. It's like a bank account. You have things coming in, things going out. There's the positive forcing by greenhouse gases. There's also some positive forcing from land use and land cover changes. And also the aerosols that are offsetting it. And of course, there's a large part that's always radiating out. Okay? So if you look at that balance, then you can ask yourself, how has it changed? So you can just integrate under the curve that gives you the total amount of energy. Okay? I want to think about it in a simple way. So this is the only equation I'm going to show you. It's essentially the total amount of energy gained by the Earth system. It is not equal to the energy part that's held, because remember, a large part is escaping all the time. So once you look at this, this is incidentally something we call cumulative radiative forcing. And if you look at that, and this is somewhat of a complex picture, so give me a minute to explain this. These are plotted in units of yotta-joules. For those of you curious, it's 10 to the 24 joules. So the total amount of energy, cumulative radiative forcing over the last century, roughly, is 3 ettajoules. Okay? So that's roughly the same as the total sun's input to Earth for 1 year. And also, if you want to compare that, that's roughly, you can see the amount of electricity we produce. There's a lot of energy that's not used. But anyway, so if you look at that, the dark part is the contribution to date from various regions. And so what you can see is, let me see if this works. Somewhere there's a pointer, I believe. Oh, here it is. Sorry, I got it. Oh, thank you. Where do I point with? On the screen? No, this is easier, I think. That's okay. That's not worse. The dark bars are what the contributions are to date. Now, if you imagine, if you were to completely turn off the emissions today, what would be the contribution from what we have already done by 2100? That's in the gray bars. If you account for the land use change, it slightly looks a little bit different. Now, different regions have different contributions because now Europe, the land use change has almost no effect because Europe deforested a long time ago, okay? And unless you're going to go back and forest it again. Then you can see the contribution of other regions. China, for example, is very small, so is India, etc. Okay, now the bottom line message from this is the current contributions include the effect of past emissions and obligations to 2100 due to emissions today are what is shown here. You can also, I'll show you a picture of what happens if you continue to emit it. But a significant amount of the greenhouse gases is offset by aerosols. The aerosols have offset quite a bit of the effect of greenhouse gases. Let's look at the contributions when you collect them together. If you look at the cumulative radiative forcing from what is called OECD countries, these are the developed countries, and compare that with what the rest of the developing countries have done, they're roughly the same to date. This very small population of the developed countries have contributed as much as the developing countries. If you do it per capita, you see it on the bottom picture. The developing countries have contributed very little, much less compared to the developed countries. And the gray areas are what we have already committed to in terms of what we have emitted into the atmosphere. Then you can do the same thing, asking yourself for a few different scenarios. We did it for RCP 8.5 and 2.6. And you can see this picture, even with whatever you do, US and Canada are not going to be the predominant contributors in 2100. Okay? China can be, with the large continued emissions, with a business as usual. But if it's RCP 2.6, China would still be less than that. For example, India is much less than that. So the bottom line message I'm trying to tell you here is it's not just greenhouse gases. Aerosols matter. And so does land use change, but to a smaller extent. The climate impact of aerosols from greenhouse gases are not exactly the same. It didn't go into that much, but they're offsetting each other. Do not forget the legacy emissions. In the long run, with continued emissions, of course, CO2 will become the most important factor. Okay? Now, a disclaimer, this doesn't tell you who is going to be impacted by the climate change. Okay? That adds a totally new dimension to the question. This is what's happening, who's contributed to the climate change, Who's going to have to live with it is another question. Now, the fact that the aerosols have both a climate impact and a human health impact is something to think about. So let's kind of think about how the same aerosols have affected or will affect humans. The detrimental effects of aerosols, you can think about, you breathe it in, you kind of got to know a lot more about it because of the COVID, which is transmitted that way. Smaller the particle, deeper it goes into the lungs. Okay? And there are lots of studies, epidemiological studies, that show you all the different ways it can affect human health, and all in a bad way. And you can calculate, based on some epidemiological exposure kind of calculations, what the effects would be. It has effect on your cardiovascular system, on your brain, and a whole bunch of other things. So let's think about what it looks like in a picture. On the left-hand side is the aerosol amounts over North America, roughly. Then over China in the middle picture, and India on the right. So just so that you know, the air you're breathing right now is roughly 10, maybe 20 times better than the air in a big part of the developing world. Okay, now what is the effect of that? First, countries like America have cleaned up. You can see from 1985 to 2015, we cleaned up the aerosols quite a bit. But if you look on the right-hand picture, there's a CWIFS image. From satellites, you can see the pollution over the Indo-Gangetic Plain in India. Now, of course, you don't want to know what's just the column amount because we live at the surface. We want to calculate what the surface amount is. So if you had monitoring stations, it would have been great, but you don't. So the way you go about doing this is use the satellite data to get the aerosol optical depth, that is the amount of aerosol between the ground and on the top of the atmosphere. You can also use another network called AeroNet, and also use ground-based measurements whenever available. And you calculate the vertical profile of aerosols, and you do some chemical transport modeling. We use GS-Chem, and then from that we can calculate the surface PM. That's what you need. Now, once you calculate that and look at, for example, India, this is the picture you see. The thing I want you to know is just because it looks kind of blue, it doesn't mean it's good. The amount you should have for good air, supposedly, is more like 20 micrograms per cubic meter. The amounts of 200, 300 is just way above, okay? But the color scale had to be this way to actually see this. The only few months in India are kind of clean. That's during the monsoon season. So this is the time to go to India. Of course, you've got a problem with flooding and things like that, but at least it will be clean air. Okay? Now you can use these things to calculate what the health impacts of these aerosols are. We can calculate the amount of people, the premature death due to exposure to aerosols, due to heart attack, strokes, COPD, and lung cancer, and the total. That's what is shown, the total is shown on the right-hand side. We calculate that roughly 1.4 million people die every year because of air pollution exposure. This is not our number only. Some other people have also come up with similar numbers. Again, I want to emphasize, death is one metric. Amount of missed days of work, other ill health effects, asthma issues, all those things are also something you have to think about. They are, okay, that's not calculated. Now, what I want to do is, when you think of air pollution, you think it's an urban issue. Okay? Because in fact, in America, we just call it urban air pollution. But let me just tell you what happens in a country like India. The picture here on the left is the night light data. And you can see the big cities. There is Delhi and Bangalore, where I'm from originally, and a whole bunch of cities. On the right-hand picture is the population density. As you can see, it's not just in the big cities. There are a lot of people away from the big cities. And these people are exposed to these aerosols too. And if you look at the population, number of people who are exposed to pollution, what you see is the non-urban people, which is in orange, and the urban is green. Of course, you'll say, yes, it makes sense. India is mostly still a non-urban country. And of course, the double hump is due to the Indo-Gangetic Plain. It's its own set of stuff. The key point I want you to look at is the two different vertical lines. The dashed line is the WMO standard for what it should be. That means India, all the time, it just doesn't meet the standard. It doesn't even meet its own national ambient air quality standards, which is the dark black line. So then if you ask yourself, what does it look like in the urban versus non-urban, the fraction of people, then actually the effect of, in terms of calculate the mortality, the urban and non-urban, there's the third picture from the left, they're almost identical. Okay? Once you calculate the fact that even though there's so many other people in the non-urban areas. But don't think it's just because bad stuff is coming from urban areas to the non-urban areas. The picture on the right shows you the rough contributions from their own emissions, urban versus non-urban. There's plenty of pollution from the non-urban areas. Incidentally, I'm using the word non-urban because the distinction between rural and non-urban is kind of tricky. So, next I want to tell you that this is not, we've seen this movie before. This has happened before. So if you look at the picture on the left, can any of you guess what these are? So that is Donora, Pennsylvania in 1948, London in 52, New Delhi now, and Paris in 2014, and this is New York City in 2023. The key message is air quality is not something you solve. You try to live with and mitigate, and you have to kind of deal with it. Okay. Now, the bottom, when you compare the effect of climate change and the health, the left-hand picture shows the climate contributions from different parts of the world, and the right-hand side shows you the health burden from different parts of the world, comparing here only with India, with OECD and USA. So as you can see, the people in India are being affected by bad pollution that has helped reduce their climate contribution. Of course, this is all wonderful, but what do you need to do to reduce this kind of pollution? One of the nice things that came out of COVID is that it's a beautiful perturbation experiment. Things changed abruptly. There are two things that happen in human civilization that abruptly changes things. One is war, the other one is the pandemic. So you can kind of guess at the amount of effort you would need to kind of tackle these issues. And what it shows here is in the left-hand picture is the changes in NO2, methane, and CO2. Actually, methane and CO2 didn't change very much during COVID. NO2 did. It's a short-lived gas. If you look at the CO2 picture, global CO2 picture, you don't even see there is an effect of COVID. There's the picture on the right there. in the blown-up picture. You can see the effect on NO2 because it's short-lived. Okay? So now let's calculate what was the impact of these kinds of COVID changes in the US and in India. So the picture here is pre-COVID on the left-hand side, post-COVID on the right-hand side, and during the lockdown and slowdowns in the middle. As you can see, it did get better in America during the lockdown, somewhat, not huge. On the right-hand side, post-COVID, the big things that happened was the forest fires actually kind of destroyed a lot of the things gained. Let's look at what happened in India. Yes, there was a change in the pollution levels from pre-COVID to lockdown, but the color scale again is somewhat deceptive. It still did not meet the air quality standards. Okay? And of course, as soon as that went away, it kind of came back. The bottom line message you can get from this is simple. You have to have equivalents or more than COVID shutdowns continuously to improve. That's kind of improve the air. So that's the level of effort you'll need to get better health benefits. So you can see this again by doing a few other things. And this again shows you the post-COVID and pre-COVID. It really was not a big deal. We thought COVID, we really stopped stuff. We didn't. Because the simplest thing, folks, to remember is we all lived through it. We had food, we had shelter, we had heating. So most of the emissions were still there. Maybe on the freeways it was a little easier to drive, but it wasn't a really big deal. So you can kind of get a feel for the amount of effort you would need to get a handle on emissions of CO2 and aerosol particles. So this is essentially what I told you. So let me stop by summarizing what I tried to tell you today. Developed countries have contributed more to climate change to date than developing countries, and that will continue to be so for the next 100 years, even if there was emission stops, unless, of course, there was negative emissions where you extracted something from the atmosphere. PM 2.5 in developing countries have reduced climate change, but at a cost to their health. And continued bad air quality is not an option. It is not something that you can live with. And as economies improve, people will demand better air quality. Right now, it is taken for granted that bad air quality is a necessary byproduct of industrial improvement, economic improvement, but it goes only for so long. Legacy is important. Future is what you have to avoid versus the past contributions that you cannot avoid unless, as I said, it's built in. Actually, the first speaker also told you about all what we already committed to in terms of ice sheets. So way forward for countries like India, you need large reductions, larger reduction than during COVID and lockdowns. Again, I didn't talk about it, but we really should never forget who is equipped to deal with the climate change. Developing countries or the developed countries. That is something for you to all think about. Thank you for your attention.